Good evening. Thanks for being here. So tonight I'm going to tell you about dark matter and the dinosaurs, but I'm really going to tell you about some of the research going on today. I just want to make it clear that this is just one possible theory. Really, there's a lot of ideas for what's going on in theoretical physics today, and really, one of the virtues of writing this book for me was the opportunity to sort of connect a lot of the ideas that I work on, which really are primarily not connecting to biology and paleontology, but really are about the very abstract or at least hidden elements of the universe that we study in theoretical particle physics, to things that are more immediate in our environment. And this book was an opportunity to sort of find ways to connect these ideas. So sort of to bring this abstract physics to sort of the realities that surround us and really understand that this really is part of our world. It's not just something that's out there. And the other reason is I really like the opportunity to tell this sort of bigger story, not just about the particle physics that I work on, but really I also work on cosmology, which is the history of the universe itself, the evolution of the universe itself, but to connect the evolution of the universe to the story of our galaxy and our solar system and even life. And really to see, you know, most books sort of approach these things one thing at a time. And the story that I was working on, the research that I was working on, was a nice framework in which to really be able to study not just particle physics, but to really connect it, as I said, down to things that are much more immediate in our environment. And although it's not really explicitly what the book's about, I do think that given the rapidity with things are changing on the planet today, it's really nice to have the context and the history and to understand what it is that goes into the environment that we have today, what it is that supports the planet and life as we know it. And to think about the fragility of some of these relations and also just the incidental nature, and really understand it as we proceed and change things. So, so both of these were sort of the opportunity. But during this talk, I'm primarily going to focus on the particular story that I'm telling that is related to my research, having to do with how, as unlikely as it might seem, dark matter and the dinosaurs might connect. So I'll tell you a little bit about that story and a little bit about the larger story in which it's embedded tonight. So dark matter. You know, it's funny how many people feel perfectly happy to tell me they have no idea what dark matter is. And it's kind of amusing because dark matter is actually one of the simpler concepts that I work on in the sense that it really is just matter. And what is matter? Matter is defined by how it interacts with gravity. So matter is stuff that interacts with gravity like matter. And in particular, it does things like clump together. So it clumps together into galaxies and galaxy clusters, into objects that we can hold or live on or stuff. And that distinguishes it from energy, like dark energy, that's just spread throughout the universe uniformly. I'll tell you a little bit more about that in a second. But for dark matter, what distinguishes it from what I'm going to call ordinary matter is that as far as we know, as far as we've detected so far, it doesn't interact with light. So it's only interacting with us as far as we know via gravity. There can be other interactions too small to have seen so far, but what we do know is that that dark matter has a gravitational influence, and that's why we know of its existence. So that means that if dark matter is made of elementary particles, billions of them can be passing through you every second, and they probably are. But you don't know about it, and that's because it's not interacting with you. Gravitational force of an individual dark matter particle is tiny, or even billions of dark matter particles is tiny. It's only when you have the huge amount of dark matter that exists in the universe that it has enough gravitational influence that we can detect its effects. So although we don't see them, it does nonetheless give shape to the universe in ways that we'll discuss. So if we look at the energy budget of the universe, we find that ordinary matter, which is labeled here as atoms, is only 5%. So the stuff that you and me and this lectern is made of is only 5% of the universe. Dark matter, there's about 5 times the amount of energy in dark matter as there is in ordinary matter. And it's funny, a lot of people get upset by that. Despite the Copernican revolution, people really want to think that everything about them is central to the universe. And it turns out it's not the case. In fact, the more incredible thing to me is that ordinary matter is as much of the universe as it is, that it's 1/6 of the matter of the universe. I actually find that amazing, because there's no reason for it to be. I mean, after all, the ratios could have been 1,000,000,000,000 to 1. I mean, I like eating pie, and any of those slices of pie, I would realize I ate some pie. But really, it could have been that one was such a small sliver we wouldn't even know it existed, and you'd be really angry because you're really just getting a crumb. But really, all of those slices are comparable, and that's actually an interesting thing about the universe, that ordinary matter, which is the stuff that we're made of, and didn't really have to be a significant fraction of the universe, is. But dark matter, nonetheless, dominates, and there's about 5 times as much of it. But most of you are probably looking and saying, why is she talking about the matter when dark energy is taking up most of that pie? And dark energy is about 70% of the matter, no, I should say of the energy in the universe. It's not matter. And dark energy was what I was referring to earlier. It's stuff that doesn't clump. It's stuff that's uniformly distributed throughout the universe. And not only is it uniformly distributed, but it also doesn't dilute. So as the universe expands, and we do live in an expanding universe, ordinary matter dilutes. Radiation dilutes. It carries less than a fraction of the energy as the universe expands. But dark energy stays the same. It's just a constant. And again, it's a large fraction of the energy of the universe. Actually, the weird thing about dark energy is the puzzle is not why there's so much of it, but really why there's so little of it. Dark energy is something that's completely consistent to have. There's no reason we can't have this energy. And the question is, why should the amount be comparable to the amount of energy we have in matter? And that is actually a really interesting question that we don't actually know the answer to. So a lot of people look at this and they get very upset. They think, look, all of that's dark, and we don't know what that is. But actually, it's an incredible story that we actually know what this is, that we actually know what these pieces are, that we understand the evolution of the universe well enough to be able to pin down that these are the components. And although we don't know what dark matter is made of, we do know very well that the dark matter exists. And in terms of ordinary matter, we do know a lot about what it's made of. We know all of this because we actually now have a very accurate theory for the evolution of the universe. People have been looking up at the heavens or the stars or whatever you want to call it for years and have been thinking about what's out there. But it really is amazing that it's really within basically the last 100 years that we actually have a true theory of how the universe has evolved. And that's because that's when we finally had a theory of gravity, general relativity, that allows us to solve the equations of given what's out there in the universe, given the matter and energy in the universe, what's happening, how the universe dilutes over time. And really, the linchpin of that was originally the Big Bang theory, which is the solution to Einstein's equations of gravity. And it tells us that the universe is expanding. In fact, that was a really disturbing thing at first. People thought the universe was static. No one had measured that it was expanding. But as everyone here knows, Hubble did measure that we live in an expanding universe. And I think that was to the great consternation of Einstein, who actually tried to add something that was akin to dark energy to try to create a static universe. But then it turned out not only was that solution not really right, but of course the universe is indeed expanding. And that's what this tells us. And as the universe expands, radiation dilutes. We start off with a lot of radiation, hot plasma of radiation. It dilutes and also goes to lower energy. Eventually, matter comes to dominate the energy of the universe. When matter starts to dominate the energy of the universe, at that point, structure can begin to form, because as you know, radiation isn't going to form structure. You don't have like light balls, but you do have matter that's able to form structure, like galaxies and galaxy clusters, and that's what we have, and that's essential to our universe today. So after matter begins to form, then we can have galaxies form as well. And then eventually we end up with our visible universe. One thing that's really interesting about this story, though, that I think people don't fully appreciate, is that the reason structure really formed in the lifetime of our universe is because of the existence of dark matter. Had there not been dark matter, first of all, matter would have come to dominate much later, and there wouldn't have been enough time in the lifetime of our universe for structures like the ones we see to form. And furthermore, dark matter is immune to radiation. after all, that's what we just said. It doesn't interact with light. Whereas ordinary matter does interact with light, so the light would wash out the structure, it would sort of smooth it out. So the existence of dark matter allows these things to form. So despite the fact that we think of it as irrelevant a lot of the time, it actually is very essential to the fact that we're all here. And in addition to all of that about the Big Bang Theory, we also know that at the very early stages, and we know this observationally by doing detailed studies of the cosmic microwave background radiation, which is a really interesting window back into earlier times. And based on that, we actually know that early in the universe, something called cosmological inflation occurred, where there was a basically explosive expansion of the universe that then went over to this smoother Big Bang Theory. And by doing detailed studies of, for example, the cosmic microwave background radiation in the sky, that's one of the ways that we know that the size of those slices of the pie that I just told you a minute ago. And I really do want to emphasize that this is not speculation. People sort of sometimes think, well, you learn things and then there's all these other questions. Well, yes, that's true. We learn things and then there's all these other questions. So we actually know there's dark matter and then we have a big question of what it is. But the fact that we do know there is dark matter and we know to the extent we do how much dark matter there is actually a really important thing. And so we really do know it exists. And we know it exists partially from studying the cosmic microwave background radiation, but we also know more directly about dark matter from its gravitational influences that we see more directly. So what would be an example of that? Well, the way we first found out about dark matter, in fact, in the 1930s, there were some observations that suggested dark matter existed. Fritz Zwicky was studying the Comet cluster. So a cluster of galaxies is a bunch of galaxies that are gravitationally bound together. And what he observed is that the speed of those galaxies was faster than could be accounted for by the amount of matter that was present. So, or the amount of matter that they saw, which meant to him that there should be some invisible matter, which he gave the name dark matter, but it was in German, so I can't pronounce it. But that's where the name started. But then, it's really an interesting story because people sort of ignored it. It was really interesting, but it wasn't trustworthy necessarily. The measurements weren't clearly accurate enough, although a couple of other people did actually do similar measurements that they also found similar things. But in the 1970s, Vera Rubin and Ken Ford working together studied the motion of stars in our galaxy. And they found that those stars, too, were moving faster than could be accounted for by the visible matter that was present. And furthermore, that wasn't true just near the center of the galaxy. It was true further away than there even seemed to be any matter at all, or a substantial amount of matter, which again argued that there was some matter that was missing. And it was originally called also missing matter, but we now call it dark matter. One of the reasons it's so confusing is because the name is terrible, because dark matter isn't dark. As you know, we can see dark things because dark things absorb light. It's really transparent matter, right? Light just goes right through it. So we now know about this matter that doesn't interact with light. It doesn't emit or absorb light, as far as we know, but it exerts a substantial gravitational influence, which is how we know it's there. There's also a couple of other ways that we see dark matter, so I just tell you about them because they're kind of cool. So we don't see it, but we do see other things. So you could, even though dark matter itself doesn't emit light, you could have a bright object behind the dark matter from the viewpoint of our telescopes. So we can be looking out at some bright object, but let's assume that there's some dark object in between, some dark gravitationally bound object. Then the light would come to us, would have to go around that object. And as we know from Einstein's theory, that object bends the light. And how the light bends depends on which direction it goes around. So the consequence is that when we look back, you actually end up seeing multiple images of the same object through something called gravitational lensing. And of course, anything could do the gravitational lensing, but if there's something where we don't see anything, where it seems dark, and we nonetheless see these multiple images, it's evidence for the existence of dark matter. And probably the best evidence that it really is matter, in the sense that we think about matter, is from things like something called the bullet cluster. So what the bullet cluster is actually comes from the merging of different galaxies. Of different galaxy clusters. And these galaxy clusters contain dark matter, but they also contain gas made of ordinary stuff. gas made of atoms interacts. So when these clusters get together, the gas of the two objects actually interacts. And because of that, the gas gets stuck in the center. Whereas the dark matter just flows right through because the dark matter isn't interacting either with the gas or with itself at any substantial level. So you really see this separation of this non-interacting material, which is the dark matter, and the gas, which is interacting, which seems like pretty substantial evidence that it is dark matter. And again, it's kind of funny because, you know, I always get these questions from people like, how do you know it's not dark matter and you just don't have the equations wrong? Well, first of all, like, modifying the equations is far more radical than assuming the existence of dark matter. Again, I just want to emphasize, the fact that we haven't seen it doesn't mean it doesn't exist. It just means we haven't seen it. So it means that it's some matter that it's not made up of atoms, it's not made up of charged particles. Modifying Einstein's equations, on the other hand, would be pretty radical. But on top of that, if you look at something like the bullet cluster, it's very hard to figure out how to modify Einstein's equations to accommodate something like this. I mean, this really just looks like stuff that's flowing through. So it is really nice evidence that there really is dark matter out there. Where is the dark matter? Well, most of it surrounds the galaxy in an enormous, approximately spherical halo. So you have the Milky Way disk made of ordinary matter, and you have this halo of dark matter that surrounds it. And that's not just true in the Milky Way galaxy. There's many galaxies that look like this, but let's focus on the Milky Way since we, of course, care about our own stuff the most. So why is there a disk of ordinary matter, though? That's an interesting question, and it's actually relevant to the dark matter story I'm about to tell you. Well, the reason ordinary matter is in a disk is because it interacts with light. And because it interacts with light, it can radiate. And when it radiates, it can cool down. And when it cools down, it can collapse into a disk. So you have ordinary matter that's collapsed into this disk. So you have the spherical halo of dark matter, and you have the disk of ordinary matter that sits inside. And so that's why ordinary matter seems to be much more substantial. I mean, in addition to the fact that it's interacting, in the region that we're sitting, ordinary matter is denser. So we have much more ordinary matter here. But there is a lot more dark matter, but it's mostly spread out in a much larger region. So again, having told the story of dark matter, I like to think of dark matter as sort of the unsung hero. You know, people are mystified by it, but again, the history of physics is learning about a lot of things that we don't see. And so I kind of have a lot of social analogies in my book, and dark matter lends itself very nicely to those. But it's like the unseen masses of society who, you know, build bridges and houses and construct hardware. We focus on the leaders and celebrities, the stuff that we readily see. But actually, these are essential to everything that's going on, and there's a lot more of them. And so dark matter is kind of like that. It formed the scaffolding of our universe. Really, as I said, structure only formed because dark matter, first of all, there was a lot more matter because of the existence of dark matter, and also because it didn't interact with light, which allowed it to collapse into structure. So really, the reason ordinary matter is here is because it sort of hitchhiked along with the dark matter. The dark matter sort of formed the structure, and ordinary matter sort of came along for the ride, which is actually an important observational thing because it's the reason that dark matter and ordinary matter are found in roughly the same region. And ordinary matter sort of lights up the region on the whole where dark matter is, because they were sort of gravitationally focused in the same regions. But as I said, although we know all of this, and it is an amazing story, and it really is, I mean, this is just part of the story, and you know, the entire first section of the book is about cosmology and how structure forms and what dark matter is. And it is an amazing story. We understand this 13.8 billion years of history very well. But of course, there are some outstanding questions, namely, what is this dark matter made of? And what do I mean by that? Well, as a particle physicist, we'd like to know, first of all, is dark matter made up of elementary particles? And if so, what is the mass of those particles? Do those particles carry charges of any sort? Do they interact with ordinary matter, even at some small level? Do they interact with themselves? But another question you can ask is it even one kind of particle? Or are there all sorts of different particles? After all, if we looked at ordinary matter and assumed, if you were a dark person and you looked at ordinary matter and assumed it was one type of particle, you'd be very wrong. Because ordinary matter is made up of quarks, it's made up of electrons, made up of muons, it's all sorts of different particles. that exist in the world of ordinary matter. Maybe dark matter is like that too. Maybe it's not just one kind of particle. But dark matter isn't the only question. Of course, we want to understand dark energy better. We want to understand why the amount of dark energy is what it is. And even ordinary matter, even atoms, which we think we understand very well, we understand the elementary particles of which it's made. There's still a big outstanding question about atoms, namely, why are they here? In the sense of, if there had been the same amount of matter and antimatter is the stuff that carries opposite charges and can annihilate with ordinary matter to form pure energy, it would all be gone by now. If we had started off with matter and antimatter in equal amounts, at this point, we would have essentially no matter left at all. Yet we are left with a substantial amount of matter. That means somewhere in the evolution of the universe, matter came to dominate over antimatter. There's what we call a matter-antimatter asymmetry. And how that came about is, again, one of the outstanding questions that we as cosmologists are asking. But the question I'm going to focus on today, and I focus a lot on this book, but is the question of dark matter. And the reason for that is I actually think it's one of the areas of research where we're really poised to make progress for two reasons. One is that there really are a lot of observations and experiments going on today that are teaching us more and more about observationally what dark matter can and cannot be. By doing better measurements, even if we don't find it, we have stronger constraints on what it can be. And the other reason is because of research like the research that I'm telling you about, which, I mean, I'm a theoretical physicist. I don't actually do the messy work of doing the observations. I care about the observations, but I don't have to do them. But I do think about what dark matter could be, what are models of dark matter, and how you could test those models. After all, these are very precise and very difficult and challenging experiments. So it really helps to have an idea of what you think it can be when you do these experiments, because if you don't, then you're not going to find it. So, but there are many new ideas for what dark matter can be, and I think there's really been a lot of work in the theoretical community with new possibilities. So I just feel like it's a place where we're making a lot of progress, and although we don't know what it is yet, we'll know a lot more in the next few years. So now I'm going to switch and tell you about not all my research, but one piece of my research, which I will tell you right from the beginning is speculative. I'm not claiming that this is necessarily true. It's a possibility. It's a possibility that we can test to some extent. So what I'm going to assume, and this is work I did with some collaborators at Harvard, is that there's a distinct type of dark matter. That is to say, dark matter isn't just one non-interacting particle, but there's a distinct type of dark matter. And it's not a big fraction, maybe like 5% of the dark matter. And that itself has interactions, and I'll tell you a little bit more about that. And what I'm going to argue is that if that's true, it can actually affect the shape of galaxies. Galaxies can be very different in the sense that they can have in them a thin dark disk in the plane, like the midplane, like the Milky Way disk. And if that's true, it really changes the nature of cosmology in a sense, and it tells you that this disk is present. And it can affect the motion of stars, and I'll tell you a little bit about that. And it can actually affect the solar system. And ultimately, as I'll describe, it could help trigger comet strikes, one of which might have killed the dinosaurs. So let me slow that down and tell you a little bit about that story. Okay. So as I said, the basic insight is really why should normal matter be the only type that's special and has all sorts of different particles? Why can't there be a little bit of richness in the dark matter sector too? And so maybe dark matter itself isn't just one non-interacting particle, but maybe there's a fraction that does interact. Now, we have a lot of constraints on how it can interact. And an interesting possibility is that dark matter has its own form of light. So just like dark matter doesn't experience our form of light, maybe our matter doesn't experience the dark matter's light, which I like to call dark light. So dark matter can interact with itself because it's charged under a different type of force, and that different type of force allows for dark light in the dark sector. So it's not the kind of light we experience, but it's its own. Now, in addition to the fact that it's not clear whether this is a simpler possibility or not, because after all, our sector is so complex. Maybe it's more reasonable to think that dark matter is also more complex. But as someone who cares about observations and testing ideas, you might say, why would I care about 5% of the matter when I haven't even seen what most of the dark matter is? Why should I care about 5%? But if you really strictly followed that logic, you would have said, I don't care about ordinary matter either, because after all, it's only 15% of the matter. Yet we do, and why do we? Well, okay, we're made of it. But there's another reason too, which is that it interacts. And because it interacts, it has this interesting structure. It forms a disk, but it has all these other interactions that lead to all these interesting phenomena. So maybe if there's this interacting component of dark matter, it too has observational consequences that make it more readily visible even than the bulk of the dark matter, and that might indeed be the case. The other basic insight, I think, for us was, I'm really a particle physicist by training, and I do work on cosmology because that also has to do with fundamental questions and fundamental particles. But what happened in doing this research is we ended up being much more interested in astronomy than we had before, because a lot of the tests of these ideas have to do with astronomy, and by astronomy I mean the motions of stars, detailed measurements of stars and the shapes of galaxies and the shapes of what's going on. It was really useful that we're coming at it from a different direction, because in reading the astronomy literature, a lot of what we were talking about was sort of dismissed summarily because people weren't thinking about it in the way we do as particle physicists and what it really means to rule something out, or what it really means to discover something. So as I'm going to argue, it changes the shape of the galaxy. There will be this dark disk, which is like the Milky Way disk. And the reason there's a dark disk is the same as the reason there's a Milky Way disk, because there's a type of light and it can radiate. And the other interesting thing is if the dark matter particle is heavier than an ordinary particle, it's actually a thin disk. The disk would be thinner than the Milky Way. So you'd have this thin disk of dark matter embedded in the plane of the Milky Way. And what's really interesting about that is that's testable, because it influences the motion of the stars in and out of the galactic plane. And one of the things that happened, so probably some of you here follow particle physics, and if you do, you know that it takes a long time to build experiments. And we've had questions for years. It took 50 years to find the Higgs boson that was proposed 50 years ago, obviously. So one of the really fun things about doing this project, which we did about a couple of years ago in the summer, was that very fall, a satellite was set to launch that was about to measure 1 billion stars in the Milky Way, in the solar vicinity. 1 billion, precisely position and velocity of those stars. And that's precisely the sort of measurement we need to test this idea. Because by seeing the motion of the stars, you can then infer what the gravitational potential is. And that tells you if indeed there is this dark disk in the midplane. And that's something we're thinking about, exactly how that testing works. So there's this thin disk of dark matter inside that Milky Way disk in this picture. And it can be tested by something called the Gaia satellite, which was launched by the European Space Agency. It was delayed a couple of months, but it launched basically that December. And this will actually test this idea of this dark disk. But, as you might have guessed, there could be other consequences. And so I'm now going to turn to considering not just the evolution of the universe, but really just focus in on our solar system, the stuff that's around our star, the sun. And so the whole second part of my book is really about the solar system. So I talk about, a friend of mine kind of joked that it sort of updates you from all the stuff that you learned in high school. Because we know about the planets, but we actually know a lot more. And it really, I have to say, in doing this research and even writing this book, and there's just a lot of stuff that we've learned. And a lot of that has to do with sort of what's sort of more dynamical in the solar system, stuff that's moved around, and even the history of the planets themselves, how they got to their current locations. And that has to do also with things like asteroids, stuff that hits the Earth or the Earth's vicinity all the time. And asteroids are basically, they really are just pieces of rock. I mean, they're not round, they're just chunks of rock. And there's lots of them. And there's more of them if they're smaller, and there's fewer of them if they're bigger. And a lot of them are in the asteroid belt between Mars and Jupiter, which is basically separating the rocky inner planets from the icy outer planets. But there's also comets, and the distinction between comets and asteroids you pretty much know, which is that comets have these volatile materials, so that although they're icy and frozen, when they get close to the sun, they form these tails that sometimes we even see. So there's something called the Kuiper Belt, which probably some of you who are following the news have heard about, because New Horizons spacecraft has recently entered there. And they're things that form short-period comets. Actually, it's not exactly from the Kuiper Belt, it's from something nearby, which is called the scattered disk. The difference is whether or not Neptune can actually disturb things so that it can turn into comets, and which go near the sun. And those are about 30 times the distance of the Earth from the sun. But much, much farther away, is something called the Oort cloud, named after the very prolific and brilliant astronomer John Oort. And that's basically thousands of times farther away than the Earth is from the sun, what's known as an astronomical unit, AU. It's like a good fraction of a light year away. So this is really, really distant. And what makes that really interesting, so this is the source of long period comets, and long period is defined by periods greater than 200 years. Now, what's really interesting about this is it's so far away that it's very weakly gravitationally bound to the sun, because Newton's law tells us that the strength of gravity decreases proportionally to 1 over the distance squared. So something thousands of times farther away has a gravitational attraction 1 over 1,000 times squared, relative to the strength of the attraction of the Earth, excuse me. And what's interesting to me about that is it tells us that if something gives it only a really small kick, it can perturb it out of its orbit. It's so weakly gravitationally bound that if there's a small kick, it can get perturbed out of the orbit. And if that happens, it could get out of the solar system altogether, or it has a possibility of coming to the inner solar system, where it has the possibility of crashing into the Earth. And stuff actually does hit the Earth a lot. Smaller stuff hits more often. Most of the stuff actually just burns up in the atmosphere. Then some stuff actually hits the Earth. And actually, the story of, so in addition to just talking about the solar system, I also talk about impacts and asteroids and comets and what we know about what hits. And actually, the story of how scientists figured out that stuff really does hit is interesting in itself. You know, people didn't really believe that at first. It sounded kind of crazy, stuff coming from the sky and forming craters. And one of the first ones that was understood was this thing called the Meteor-Barringer crater. And it actually accidentally just happens to be quite near where there's a lot of volcanoes. So people thought it's a volcanic crater, except for Mr. Barringer, who was actually a mining engineer and a businessman. And so he thought it was actually an impact crater. And he furthermore thought that he was going to make a lot of money, because he thought that, you know, this thing hit. And one of the interesting things about the stuff that hits is that, so whereas things like iron go to the center of the Earth, there's stuff that, if stuff hits, it goes to the surface of the Earth. So it can be a source of gold and iron and other kinds of elements. So he thought this was going to be a great source, not realizing that stuff mostly burns up on entry. He did, however, so he invested a lot of money, and he did show that it actually was an impact crater. And the whole story is really interesting, because people were trying to scientifically show that it was or was not an impact crater. But they didn't understand how impact craters formed at the time. So for example, somebody named Gilbert thought it was an impact crater, but he thought he would look at it very scientifically. And he thought, well, if it's an impact crater, something came and hit it. So it came from some particular direction. So it came from some particular direction, you wouldn't expect it to be round. And he looked and he saw it was round. He said, well, my theory was wrong. It's probably just a volcano. The reason he was wrong is because that's not how impact craters form. It turns out what happens is it hits the Earth, compresses it so much that there's a shock wave, and that shock wave is actually what forms the crater. And so that's why it's round. So actually, and one of the great things that's on the internet is something called the Earth Impact Database, which actually is a list of all the impact craters that have been found on the Earth. And it tells you their size and their age, which was very useful for my collaborator, Matthew Reese, and I, when we were trying to do our study. Because we had so we were investigating a proposal, not just that killed the dinosaurs, but a proposal that large impacts happen on a periodic basis. We weren't the first people to come up with this idea, in fact. But people had thought that looking at the data, there was some evidence that large impacts happen on a periodic basis, where by periodic, I mean on the order of about every 30 million years. Originally, it had to do with trying to look at extinctions, but then just looking at the crater record itself seemed to indicate that. And it's actually a very dicey story. Some people say it's true, some people say it's not. And the reason is obvious. It's because the crater record is very sparse. Because most stuff doesn't leave a mark. In fact, most things that hit the Earth, even if they hit, are going to fall in the ocean, which covers most of the surface of the Earth. And stuff that doesn't fall in the ocean can get eroded over time because the Earth is geologically active. So it's not clear what fraction of these things we find. And in fact, we decided to look at things that were 250 million years old and bigger than 20 kilometers, meaning that it was formed by something about a kilometer big that hit the Earth. And there's only about 26 of them. So that's a pretty sparse record if you're looking over 250 million years to look for a 30 million year period. But you can nonetheless try to do it. And actually one of the advantages, as we are in the book, is of actually having this model, and I'll tell you what that is, for why these periodic impacts should happen, is that you can do it on a firmer statistical basis. So why should there be periodic strikes? And here's where the whole story comes together. So the solar system, which includes this Oort cloud, goes around the galaxy, and it goes around about every 240 million years. And as it does so, it bobs up and down slightly through the plane of the Milky Way. So, and how often it does that depends on how much matter is actually in the Milky Way plane. So if there's no dark disk, that would happen about every 55 or 60 million years, which doesn't agree with what has been observed in the crater record. However, if there is a dark disk, there's more matter, and it can be a 30 million year period. The other advantage of having a dark disk from the point of view of trying to explain periodic comet strikes coming from the Oort cloud, again, this is because there's a sharp gravitational force that happens as you cross the Milky Way, which is much denser. And particularly if you cross this dark disk, it's very dense and can dislodge objects from the Oort cloud, giving that extra kick that gets these weakly bound objects out of their orbits. They might, on a periodic basis, be more likely to come hurtling towards the Earth. And so the idea is that every time it passes through, there would be this possible dislodging of comets, just on a statistically higher basis, that can come towards Earth. And so you would predict that there would be a 30 million year, approximately 30 million year periodicity. It's more like maybe 32 million years. It's not that, the record isn't accurate enough that we really know. But I remind you that when the dinosaurs died, along with 3/4 of the species on the planet, was about 66 million years ago. We happen to have gone through this plane about 2 million years ago, which means it won't happen for another 30 million years, so those of you who are worried can relax. But if the period is 32 million years, it means that one of these could have happened because of this dislodging of an object from the Oort cloud as it passed through the dark disk. And this aside, another thing that I was really thinking about when I wrote this book was just learning about extinctions and the evidence for it. It's really fascinating how much is there. Although any individual fossil might disappear, there's just so much life on Earth that there's actually a pretty strong evidence in the fossil record, and there's really been 5 major extinctions. And just as an aside, I think it's really useful to think about those extinctions when we think about what's happening today. I mean, there is evidence that we might be actually in the middle of a 6th extinction that's really caused by humans. And it is interesting to compare the conditions. Not all of them were caused by things hitting the Earth. In fact, the only one that we know for sure was this one 66 million years ago. And the story of how that was understood is also a great story. So I tell you about that too, about how we learned that this extinction did happen and that it was an impact. And also how the actual impact crater was found. And again, you know, when people suggested that there was this impact, the odds were against finding it because, again, most of the stuff ends up in the ocean. So it is an amazing story of how actually people who were actually working for a Mexican oil company finally began to talk to scientists who had done some geological surveying and found this circular structure in the Yucatan that was not actually of interest to them because they were looking for oil. And, but then they could talk to people who were actually looking for a crater and actually put this together. So that we now have really, when I first started this, I mean, I'd heard about this impact hypothesis, you know, it's come out, you know, during my lifetime, but I didn't realize how strong the evidence is. We now know that that crater was formed within 20,000 years of the time when the extinction happened, which is, you know, for something 66 million years ago, it's basically the same time. I mean, it's very clear that the two are connected. And it's also just amazing how many bad things can happen when something that big hits the Earth. It was something 10 to 15 kilometers big, you know, 3 times the width of Manhattan, hitting the Earth at 40 kilometers a second. It was basically every disaster scenario that you have in movies, except for a zombie apocalypse, which happened. So I just want to say that one of the reasons we do model building is because if you don't know what you're looking for, you usually don't find it. And I like using this picture because it's just kind of fun. When I have some friends who are, work on the Big Bang Theory, and they're writers, and I was going to visit, and they said, why don't you just act like an extra and just sit in the lunchroom? And so, and literally the directions I were given was to be inconspicuous. So I was apparently so good at my job that most people didn't realize I was there, even though, if you can see in this picture, I'm like right there behind the people. But people never expected me to be there, so they would never look. And I actually do think that's a nice metaphor for what's going on in science, because really, when you're doing these detailed measurements, unless you know what to look for, it's very easy to overlook things. We can talk all we want about big data sets and try to put together information, but it really helps to have models to know what you're looking for, because then you know how to test for it and you know how to find it. So even though this work is speculative, I think it's really important to know. The Gaia satellite is doing these measurements whether or not we have this model. So it's really interesting to know that one of the things they can test when they're doing it is this idea of a dark disk within our own Milky Way. So I just want to say that I've focused on this particular story, but really this book is sort of about all the amazing connections that exist in the universe and really how we got here. I just list a few here. In addition to saying, as I did earlier, how cosmos and the galaxies really formed from dark matter collapse. Just the things like carbon coming from star burning is probably something many of you know, that it comes from supernova. What I didn't know, for example, is that for something like the size of the sun to form, you have to have such cool temperatures that requires molecular cooling, which is an amazing thing, but it requires molecular cooling with the heavy elements. And without that, things wouldn't have cooled enough that something the size of the sun could form. Here's another interesting thing. Our planet's geology, and hence the carbon cycle in life, that is life. That is to say, plate tectonics that put carbon into the atmosphere and take it out, of course, relies on nuclear processes too, because that's what's heating the mantle. Nuclear decay is heating the mantle, which is allowing plate movement, which gives you the rise to the carbon cycle. You don't often think of it that way, but these connections are really there. And of course, the one that I'm suggesting now, which may or may not be true, is that this extinction might indirectly have been triggered by dark matter, which really dislodged something from the cloud. And I remind you that large mammals emerged only after the extinction of the dinosaurs, who were taking up a lot of the resources. So it could be that our very existence had to do with this dark matter trigger, getting rid of the dinosaurs and making room for us. So in the introduction, I talk about 4 major lessons, which I think resonate throughout the book. For me, just understanding all these connections. I think this both just the beauty of how all these things fit together, how the stuff that we see on Earth today. I really do look at things differently as I walk around, realizing where things came from. And also just wonder also at the fact of how much we've been able to figure out. I'm not saying we've answered all the questions, but it is amazing how much of the cosmic history we've been able to put together, and how much of the more immediate history about life and the planet. One of the really interesting things also about some of this research, and in particular the story of understanding the extinction of the dinosaurs, was really how many fields of science came together. Walter Alvarez was a geologist, was studying timing, worked together with his father, who was a physicist, to put together some of this information. They worked together with chemists to be able to study radioactive decays. And of course, there's other geologists and paleontologists who put together all this information. And of course, if this story is true too, cosmology enters as well. So I really like the way it integrates all these different fields of science, which of course really are part of the universe we live in today. Another interesting lesson is just how recent is our understanding of a lot of this stuff. Many of these developments happen within the last 50 years, and almost all of them happen within the last 100 years. It is amazing how much we've learned so recently. And as we're learning it, how much we're changing things. And so I'd say the final important lesson, which again resonates through a lot of science, is sort of the rate of change. Sort of gradual evolution versus sort of very quick evolution. And that's true for evolution of life itself. One of the major debates was, do things happen slowly or do they happen rapidly? People like Darwin thought all evolution was gradual. People like Cuvier realized that something as dramatic as extinctions happen, which people really didn't realize in the beginning. And so just the combination of the two and how they contribute to the evolution, not just of life, but of our planet. But also the speed with which we're changing things today, I think is a very important thing to take into account. So I'll just end with a couple of pictures, which just, for me, gives some idea of the beauty. So when I was visiting the University of the Basque Country to actually give a physics lecture, they know I like the outdoors, so we went on a little hike by the beach. And as we were doing so, one of my colleagues said, oh, my cousin's a geologist. And she told me that the KT boundary, the KPG boundary, is right nearby. So the KPG boundary is really what told us about this extinction 66 million years ago. It's this amazing layer that's really all over the globe, that you can find pieces of it all over the globe, where there's sort of lighter limestone separated by this clay from darker limestone, indicating that stuff that was alive at one point suddenly disappeared. And so it was just an amazing thing to find out that this was nearby. So we actually organized an outing for the next day, and we went to visit. And this is the director of what's known as a geopark there. And as if that isn't enough to be able to go there and actually just go to this boundary, which was a lot of fun. It actually is in one of the most beautiful beaches that I've ever seen. So it really was a fantastic opportunity. So I just want to say, I don't know if the dark disk is right, and search for it is ongoing as we speak, but I do know that these amazing connections really are there, and they lead to essential to the universe and ultimately to life. So I'll say if you want to read about more of them, this is the place to go. So thank you.
So we have time for some questions. If you have a question, raise your hand and wait till one of us acknowledges you, and then come to the aisle to ask your question.
Question over here, Lisa?
You only addressed dark matter as it pertains to disk galaxies. Do you have any remarks regarding dark matter and how it plays with elliptical galaxies that don't really have a center?
So it's really a similar story. So here we talked about nice rotating stars, but really the speed of stars is always determined by the gravitational potential. It can be determined in different ways. So it's more like the original measurement, which was in the Coma cluster, where you measure the virial velocity, if that means anything to you. So it's just the velocity that's allowed by the gravitational potential.
Next question over here.
Is it possible that the dark matter interacts so much and radiates in a flight it could form something akin to dark planets, or is it more like spread out like nebulae?
Well, this is just really the first step in this kind of research. I mean, once you allow for this possibility, it's not clear that, you don't even have nuclear forces, you don't have other kinds of forces. So all these things are possible. I can't promise you, but I mean, as you add more assumptions, then you have to think hard about how to test it and whether it's true. But they're all possible.
Next question on this side.
Hi there, Lisa. Back when I was a student with Stephen Jay Gould studying evolution, it was called the KT boundary, and I noticed you almost called it that, but now it seems to be called something else.
I know.
Did nomenclature change? Yeah,
so it's really funny. So they used to have 4 kinds of, eras. So there was the tertiary, but for some reason they didn't like the tertiary. Now it's called the Paleogene. So it's really funny because the quaternary still exists because it had its strong supporters. But the tertiary didn't have strong backers. So it's now called KPG, which doesn't sound nearly as good.
Next question up here.
What do you expect us to learn about dark matter in terms of what it's made of in the next 5 or 10 years? You said it was an exciting time.
Well, so it really depends. I mean, this is a cagey sounding answer, but it's true. It depends what it is. Because there are lots of observations going on. And if it does have some small interaction with matter, we will know about it. If it doesn't, we won't find the particles. I do think we will know more about whether it interacts with itself, because that really changes the shapes of galaxies. So, meaning even if it's this component or if all of it has some self-interaction. So we'll certainly learn more about that by a lot of these big astronomical observations that are going on. But I can't promise you that we will know fundamentally what a dark matter particle is.
Next question on this side.
Is Large Hadron Collider helpful at all learning about dark matter and dark energy?
Yeah, so it is if dark matter is this thing that interacts a little bit with light. So there's a reason to think that it could be. If dark matter has about the same mass as the Higgs boson, and it's stable, which it would have to be, you'd have just about the right amount of it left today to be the dark matter. I mean, one thing we do know is how much energy is stored in dark matter. So you can just follow how much it would have annihilated, and you find that that's about the right amount. So for that reason, people think that maybe it is somehow connected to the standard model of particle physics. And if that's true, it could be conceivably be produced at the Large Hadron Collider. I mean, so far we haven't found any extra particles there, but it's a possibility. And that's one of the things they're looking for.
Next question up here.
Yes, thank you. Black holes being such strange creatures as they are there any theories that they may have some special connection to dark matter?
So, you know, it's funny. Everyone thinks of black holes when they think of dark matter. But in this case, so black holes are just formed by lots of energy that gets into a small region. So that energy could be ordinary matter. It could be dark matter. It sort of loses track of what it was. So yes, dark matter could have contributed to black hole formation, but so can ordinary matter. So they really are two independent entities.
Next question up front.
Hi. For the observations that are going on, how can a layperson or a non-physicist be able to observe what's happening, sort of like citizen science?
So this is a little bit self-promoting, but I mean, one of the reasons you write the book is so that when there are news stories about it, you can have, I mean, you're not going to be able to explain everything that's going on in a news story. So I mentioned some of the experiments that are ongoing in the book, but also what they're trying to do. And then it's just, you know, following it on the web, or there's a lot of, actually, Twitter is really good about telling you when there's new results, too.
Next question to your right.
Thank you for a fascinating talk. You mentioned that dark matter is not subject to interaction with electromagnetic radiation. Does that also imply that it's not subject to the 299, et cetera, 1,000 kilometers per second limit?
No, because that just has to do with more the nature of it's hard, sort of the nature of gravity, or the nature of the laws that underlies all of kinematics. So it's, I mean, the thing is, light is not the only thing that travels at the speed of light. Anything that doesn't have mass travels at the speed of light. And that's just the limit, as far as we know, to how fast things can travel.
Next question on this side.
So can black holes swallow dark matter or dark energy?
Black holes can swallow dark matter. Again, dark energy is sort of spread out, but dark matter can certainly go in and be eaten up by a black hole, and the black hole gets bigger.
Question up here.
How many of those 32 million years are spent crossing the disk?
That's a good question. And it's probably, for it to match the data, it's probably about 1 to 2 million years. I mean, things don't happen immediately. Things get dislodged. They have to come, you know, it eventually enters into the solar system. So there's sort of a period afterwards when things are dislodged, but it's probably within about 1 or 2 million years.
Oh, okay. The other mysterious kind of matter is antimatter, and I was wondering if...
That's not really mysterious.
Okay, well, maybe well, there is a mystery in that about the equality of the...
That's true. So the question isn't just what antimatter is, but the question is how there's more matter than antimatter.
I was just wondering, does dark matter give you any insight into antimatter, or also does the kind of dark matter you're talking about, because it has interactions, possibly have anti-dark matter?
Yeah, so that is actually a really good question, and the answer is yes. Because to get the right amount of the dark matter, you probably need a dark matter, anti-dark matter asymmetry, the same way you have a matter-antimatter asymmetry. And one reason people think about things like this is because of what I said early on in the talk, that there's a similar amount of dark matter and ordinary matter. So maybe they were both formed in a similar way. So maybe there's a dark matter, anti-dark matter asymmetry, the same way there's a matter-antimatter asymmetry. And they're connected.
Question up here. Sorry about that.
I read recently about Pluto's moons and their erratic behavior, and I'm wondering if dark matter can be linked at all to such observable phenomena.
It could conceivably be. It probably isn't. I mean, probably we just don't understand yet how those moons are bound together. But I don't think we know the answer to that yet. I mean, basically, it seems to me, I mean, I'm not an astronomer. It does seem to be every time there's a more detailed astronomical measurement, you read an article saying things are shocking and surprising, which means we just didn't really understand it as well as we hoped we would. And we figure more out when there's observations.
Okay, we have time for one more question, and I just want to remind everybody, I'm sorry, I see that there's 2 more on this side. We'll take them. So 3 questions, one on that side and then these 2,
But
sorry.
we only have time for one.
Reminder to everybody to join us immediately afterwards where Lisa Randall's going to be signing books in the atrium with cookies.
All right, question over here.
This is a pretty down-to-earth question. Can you talk a little bit about the craters and what value they still have for being explored? Are craters actively being studied now? And particularly if you have any knowledge about the Mitzpe Ramon crater in the Negev?
I have no information about that particular crater. But basically, when there are craters, people study them. They try to date them more accurately. They try to measure their size more accurately. And people try to do that right away. But with things like the crater in Yucatan, I mean, they went back and studied a lot of stuff about the geological features surrounding it because we knew so much about what had happened that time. And in general, that happens too. I mean, there's a crater, but then you'll study a lot of the geology nearby. You look for particular things indicative of an impact and try to figure out, ideally you'd want to know, was it an asteroid or a comet that hit, and can you learn things about what kind of, most of the stuff burns up, and maybe it leaves some things, and you have some meteorites. So people do study that. I don't know the details about that particular one.
All the way in the back.
Okay, I wanted to know 2 things. First of all, if you could weigh that central dark matter disk, perceivably that 5% of dark matter that interacts with light, weigh it versus the weight of the baryonic matter in our galaxy. How might they compare? Because you mentioned that the dark matter candidate might be a very potentially heavy element. And then second, more than that, because I can get your book, but second, I read a lot of book, right? Yeah, I am going to get your book after I put you through this next one. Alan Guth, with the inflation theory at 10 to the minus 43rd second, pretty much figured out that the universe expanded. And from that, it came on with string theory that there might be alternate universes because if it's expanding in one area, the larger scalar field would pop off with other bubbles, nearby bubbles. And they have searched for an imprint in the Antarctic. They've searched for an imprint in the microwave background radiation for a potential collision between the two, which hasn't been found, and it was turned to be just background noise. But my question is, if you take a look at Andre Lin's bubble map and Max Tegmark's multi-dimensional map, that everything that could happen somewhere has already happened somewhere simply because of the large amount of real estate, the bubbles side by side, and the fact that within each bubble, the sum of all paths says that everything could happen has already happened, which means we've had this conversation trillions of times before. I don't believe that because every grain of sand in every ocean would have to have an alternate universe. Even though it's 10 to the 500th alternate universe, there's only 10 to the 86 particles in the universe. So do you believe everything's already happened already?
No. So if the answer to your first question is a 6, the answer to the other question is no. The reason I don't believe that is because I think it's too facile to say this thing of everything can happen. And I think, first of all, as you say, things are finite. But more importantly, there's different kinds of infinities. So you have to do the limit carefully. So if you think of all the circumstances that are required to get things, it's just having an infinite amount of stuff doesn't mean that every kind of infinity can happen, because you can take limits, and that's a more mathematical thing that we can talk about. But I think it's just much too facile to say it, but it sounds good, and no one's going to prove you wrong, so why not? But there's just lots of things that can happen that don't happen. Thank goodness for that.
Okay, and the real last question.
Thank you. So it should be a little easier than the previous question. So you showed a pie chart earlier showing that it's 5% atoms, 26% dark matter, and 69% dark energy. So I'm wondering if this is changing as the universe expands, and if it is changing, what are the implications?
Yeah, so the implication is that, so matter dilutes, and both the 5% and 26% dilute at the same rate. There's actually a tiny amount of radiation that was so tiny that's not even there, and that's going to get even more dilute. So that stuff's going to dilute. So in a while, that dark energy is going to dominate more and more over time. So eventually, dark energy will be everything, and the universe will be pretty much empty.
Okay, thank you all for coming, and especially to Lisa Randall. Thank you.